Welcome. I will talk about Deoptless. Deoptless is a technique in a JIT compiler to avoid de-optimizing when there is an assumption failing. So let's start with a simple explanation of how a JIT compiler works. So here's a bit of code that our user wants to run. It's a function that takes an argument, scales it by a factor. So first thing we do in this prototypical JIT compiler is we take that code and compile it to bytecode. And we have an interpreter that executes this code for us. So now we're running that code a lot and spending a lot of time interpreting that very generic function. So one thing we want to do now in the JIT compiler is take the code, optimize it to native code. But the point is we don't just want to translate this generic version to native code, but we actually want to use the dynamic information. So what is going on here as well is that we will record dynamic profiling and we'll use that dynamic information for optimizations. So this is what's going on here. So as a sort of bit of a silly example, let's say our profiling says that this global variable factor happens to always be 2. So I can do strength reduction, convert the multiplication into an addition, and I have code that runs much faster. But now this is code that is optimized under an assumption, right? And it could be wrong in the future. So there might be some later part of the code of the program that we haven't seen yet, and it might turn out to not be 2 forever. So what compilers do in this case is a technique that is called OnStack Replacement. And it literally means that. So we take the native execution frame of the code, we rewrite it to a corresponding bytecode interpreter frame and just continue as if nothing had happened. All right, so far so good. So let's look at how this looks in practice. So we start out with our generic scale function that works for any type, right? So we execute this for a while until some heuristic triggers. It tells us, okay, the factor is always 2, so let's optimize for that. So now we're really fast, and eventually, well, the factor changes. So we drop down back to the interpreter. We have to collect new information. Maybe we see, well, the factor changes once in a while, but it's always a number. So let's optimize for that. 2 issues here. One, it's a bit strange to the user that suddenly the program becomes really slow after it's sped up initially, right? That's the first thing. The second thing that is a bit annoying is that the final version, the sort of steady state stable version now is slower than it was intermittently. And that's also very annoying to the user. So what could we do instead? Let's look at this deopt here and zoom in. So what we actually want to do here is we arrive at the point where an assumption is wrong. And we now would like to have a new primitive that allows us to essentially not go back to the interpreter, but correct our mistake on the fly. Let's say, oh, here now I want to have an optimized continuation for when the factor is 3, or I want to have one ready for when it's like some arbitrary number, and now I can just use these optimized continuations to recover. So that's the goal. Now, of course, the question is how to do that. So to explain you how we do this, I will start with an explanation of how OSR works, or how I think we should explain how OSR works. And from that, we naturally get to Deoptless. So OSR. So this is, again, our native code here with the assumption and the speculative optimization applied. Here we have the bytecode version, the generic one. And now the question is how to get from the right to the left, how to rewrite the native state of our CPU and rewrite it into an interpreter frame such that the interpreter can continue as if nothing would have happened. So it's easier to understand this transition if we chop it up in simpler steps. There is the first step is we extract the native state. In this step, for example, we need to know that register 1 was mapped to the variable x. Then we undo the optimization. And in this step, for example, we know how the program states are related. We know how to reconstruct the missing, the things that we optimized away. For example, here, On the right-hand side, we don't have a factor variable anymore. So this is that step. And then the final step is we synthesize an interpreter frame. And now it seems to get a lot more tractable. Let's put this on the side. And yeah, now Deoptless. We don't want to do this. We don't want to go to the interpreter. So what could we do instead? We could take that de-optimized state and re-optimize it again. So we start there and we compile or we optimize an optimized continuation starting from that point where we made the wrong assumption. And then instead of synthesizing an interpreter frame, we synthesize native state corresponding to that point. And now this might sound complicated, but in fact it's something that is already solved. So this is OSR in. Every JIT compiler out there does this when they get stuck in a long running loop. For example, in interpreted code, then they will be able to transition to native code at this point. So if we put all of this, put it together, OSR out, OSR in, and of course we don't want to do this every time. So we do that once. We keep all the optimized continuations around, and then we use a bit of previous work that is called context dispatch, and we use that to dispatch to the optimal continuation under the current circumstances. So now we can have multiple of these continuations. Let's say I have one example where the factor was a floating point, one where it was a complex number, and we use context dispatch to basically select the most appropriate one or the best one. And I don't want to go into details here. You have to read it up. So let's look at an example from our implementation, what we could do with this. The implementation was done in R, which is a JIT compiler for the R language. And here we have sort of this prototypical example where we have a global data vector, and we want to summarize the elements of this very naively. And I just show you the full graph of running this example. And you can see always four. So at the top, you see the normal execution. At the bottom, you see the Deoptless execution. And then you see 4 quarters of different types and 5 iterations each. So that was too much. I'll go step by step. So let's say in the normal execution, I start with integers. And we see sort of the normal warm-up. So it takes a bit of time for the compiler to realize what's going on. And then we speed up. And finally, we have a very efficient implementation or a very efficient version for this. Then we change the global variable to contain floating points, right? And now our assumptions failed. And the code has to be replaced, and it's replaced by something that is optimized for any kind of number. And now the numbers are boxed, and as you can see, it's slow. Here, we change it to complex numbers. The compiler gives up. It puts a version there that is optimized for any type, and we're even slower. But what I in particularly want to point out is in the last quarter, we return to integers. So we set data again to contain an integer vector, but we've destroyed the performance. Like we're now slow forever because once we have seen this different type, right? Now let's look at Deoptless. Here, the beginning is exactly the same. Second case where we put floats or reals, as I wrote here, we execute up to the point that I have highlighted. At this point, we realize actually the types changed and we should do something for reals. But instead of replacing the whole function, we will just compile a continuation starting from that point to the end that is optimized for reals. And as you can see, there is a bit of dispatching and OSR overhead, but overall, we're much faster now because we're really specialized to this situation that occurred. For complex, not much better because, again, the compiler doesn't have optimization for complex numbers. And finally, if we return to ints, then nothing has happened. So we still have the same code. The OSR doesn't trigger, so it's the same as in the beginning. So evaluation was surprisingly tricky for this paper because, well, deops are by definition, very infrequent events. And in particular, if you run a compiler, or if you run like a standard test suite that is used to write the compiler, then you won't find many deopts in there. So we had a couple of example programs, and these example programs, we knew that they had phase changes in them, and we evaluated it on these programs, showed some effects there. We compared it with a sampling-based re-optimization approach. So this was also prior work where this stale type feedback was detected with sampling. And finally, we had a synthetic benchmark that I think is interesting. So what we did there is we ran the whole test suite and we randomly triggered the optimization. So basically we said 1 in 10,000 cases where we have an assumption, we will fail it even if it holds. So this is sort of the worst case for the compiler because there's nothing to be gained from this de-optimization. And so then we measured how well Deoptless can, or how Deoptless improves the execution times if we do that. Well, in fact, I should say how much Deoptless fixes the regressions introduced by this randomly de-optimizing thing. And here we can show that this will lead to 1 to 10x faster recovery in these cases. Okay, so to put it all together, Deoptless is basically the combination of OSR out, OSR in, and context dispatch. It is very simple to implement on top of a VM that already has OSR out and OSR in. In fact, our implementation was around 300 lines of code. Yeah, thank you.
I was with you until you put up the experimental results and said we had trouble finding examples of that. Does that also mean that there are not many examples of this out there in the wild in our code, that basically, you know, the optimizations that were previously in JITs, which assumed that, you know, once you figured out what the type was, it didn't change very often.
Right.
Are basically the ones you want to do?
So two things. So you can be more aggressive with these kind of fallback strategies. So you have to, you can be less conservative in when you start to speculate. And secondly, it's not, I don't think the number, the frequency is the important thing, because these cases where as I showed in the beginning, the performance is really erratic. Those are pathologies and they're very annoying for the users. So they do occur in practice, and even if they only occur very infrequently, it doesn't really matter, because if they do occur, then it's very erratic, right?
You said continuations a few times, and I'm not sure what you mean. Do you mean something like the content of the instruction pointer and registers, or?
Okay, what do I mean by continuation? I mean that, so the OSR event happens in the middle of a function. So basically it's so yeah, literally continuation. So the OSR extracts the state, right? And then a continuation using that currently extracted state to the end of the function. Yeah.
Okay, thanks. And another quick question.
But what gets cached is just the code, of course. Right?
Yeah. Do you, at some point, garbage collect these specialized versions?
Good point. Currently not. It could be done. Yeah. So we use LLVM as a code gen, which doesn't even allow you to remove code. But that aside, it could be done.
Okay, another question from Slack. Is there any relationship with the lazy basic block versioning technique of Chevalier, Bossenver, and Feenley from 2015?
Yeah, I think it's a great question. And yeah, yes, there is a relation. I mean, basically with basic block versioning, you do this at every basic block. And here, we're using it for speculative optimizations, to recover from speculation, from misspeculation, and we only do it when it's needed. So okay, that was not a good answer, but I mean, at the heart, many things can be described as an instance of lazy basic block versioning. So I think that was a great framework that she introduced to think about these kind of optimizations.
So you don't get rid of the extra code that you generate for other situations. Do you have any numbers about how much extra code that is, or how much extra memory it takes up?
Yeah. So we try to measure it. The problem is R is so inefficient that actually producing optimized code is almost always a win, because you get because the program itself will use a lot less memory. So when we measured it, we ended up always with a net win. And we didn't measure the code in isolation yet.
All right, let's thank the speaker.